In differential calculus, we study about one independent variable and more than one independent variable. So similar way we have for integral calculus. Integral calculus. So we already studied the definite integral. So this is the extended form of the definite integral that is called multiple integral. That is called multiple integral. Multiple integral, and we can say that the repeated integral. So in multiple integral, we have more than one integral. That means with respect to x and with respect to y, we have function of xy. So we define as, so let fxy be a function of two variable defined as the point in some finite closed region. In xy plane, A be the area of the curve so we subdivided the area of the curve into n equal parts. N equal parts. So then we write down the limits write down the limits of the area which is bounded for the function fxy over the region A which can be denoted as double integration over the region A f of xy into dA. So here the function fxy is continuous and limit exists. So this is the necessary part exist at all points within and on the boundary of the region A. So we have a xy plane. So this is our x-axis origin and y-axis. So we can take any curve, okay, whose ordinates we can take in this way. So that means here is a x-axis, x equal to a, 2x is equal to b, and some ordinates are given for y. So here is we can take as y equal to a to y equal to b. Y equal to a to y equal to b. So first we write down as if both the ordinates or both the limits are constant, both the limits are constants. So when both the limits are constants, so we integrate, write down this form: x is equal to a to x equal to b, and y is equal to a to y equal to b, function of fxy into dA. dA, we take a small strip, that means this is dA. dA, we take a small strip. So the area of the small strip is length into width. So dx into dy, the variation or change into this one. So we have this dx and here length dy. So area is dx dy. So dA we denoted as dA is equal to dx into dy. So you remember this one. So now we can write down as x is equal to a to x equal to b, and y equal to a to y equal to b, f of xy dx into dy. Okay. So we can change the limits here also. So you can take as limit as c to d. So there is no issue. So here we are discussing the general formulation. So when we take the limit of c to d, so you can do that. That means in place of a, we can put, because we have taken the limits as a to b for x. So you can take as for c to d. So we can express this as, so when we take limits of y as c to d, limits of c to d, so then this can be written as integral x is equal to a to b and y c to d, f of xy into dx dy. So this is the double integration form. Here both limits are constant. So we have already mentioned here, so both limits are constant. So when both limits are constant, now we talk about the integration. So when both limits are constant, so how to integrate that? So for integrating this thing, so we write down as, to integrate to integrate left to right. That means we basically read as left to right. While the corresponding integrals with appropriate limits as read as right to left. So first, basically, we identify, that means integrate left to right. So basically, we integrate left to right. So left to right means this is the left hand side, we can read as, or here is the, we move to the right hand side. So we follow this thing. So that means first integral. So as per the dx dy, so first limit will be for x and second limit will be for y. So when we write this thing, so when both limits are constants, so then we can integrate any one of them first. We can integrate any one of them first. Suppose we are integrating with respect to y first. So we treat x as a constant. The same rule we have followed in differential calculus, that means partial differentiation. So when we are going to differentiate partially with respect to s, to treat y as a constant for two variables. So similar case for the double integration. So when we are going to integrate with respect to y, so we treat x as a constant. Or we integrate with respect to x first. So then treat y as a constant. So these are the basic rules, so you have to remember. So now this is the case when both limits are constant. So now we further move for the variable limits. So now we talk about the variable limits. So it is clear that one limit will be variable and one limit will be constant in double integration. So now for one limit is variable and one limit is constant. So when one limit is variable, one is constant, the variable limit which may be for y or which may be for x. So suppose we take as if limit of x is given as x equal to a to b, limit for y is given as y equal to f1x to f2x. So here the limit of y is variable in terms of x. So we write down dx into dy. So such type of cases when we solve, so first we solve the variable limit. So in such cases, so here we write down as first we solve the variable limits. So in such cases, first we solve the variable limits. So how to write this as? So we can write this as x equal to a to b. So first we solve the variable limits. We write down as y equal to f1x to f2x, f of xy into dy and dx. So first we solve the variable limit. That means first we integrate with respect to y. First integrate with respect to y first. So integrate with respect to y first, then we integrate with respect to x. Okay. Now, second case or maybe occur in this form. suppose y limit is constant. So y limit is y from a to b, and x from f1y to f2y. So f1y to f2y, f of xy and dy dx. dy dx. So here the limit of x is variable in terms of y, or y is constant. So now first we integrate with respect to x. So first we solve the variable limit, then we solve the constant limit. So when we solve first for x, so we write down f to y, f of xy into dx, and write down as dy. So first we solve with respect to x. So in this cases, so first we integrate with respect to x. So hope you understand. He's so you can see that means which type of cases arise for that means here we have a curve. So we write down the ordinates in this form, and we take the elementary strip parallel to y-axis. So when you take elementary strip parallel to y-axis, so suppose the boundary of the this curve we write down as f1x, and here is the f2x. So boundary of this curve, and the ordinate given as x equal to a to x is equal to b. So ordinates of x is purely constant, ordinates of y is variable from okay. So along x-axis, so y will be 0, along y-axis x will be 0, and we have a curve. So this curve we denoted as f of xy, and the boundaries, so which we can take as f1x to f2x. So the strip we are using from f1x to f2x. So we can take a limit as variable. Similarly, for variable y, so we can revolve the elementary strip parallel to the x-axis. So you clearly understand that when a limit is variable for x or y, so the elementary strip is parallel to x or parallel to y. Okay. So after understanding the limits and concept of the double integration, so we move to the problems related to that. So we start with the first problem related to multiple integral. So problem one is that we have a question: evaluate integral 0 to 1, 0 to 2, x plus y dx into dy. Okay, so we have already mentioned that means we move from left to right. So we move from left to right. So left to right means as per the order of this dx into dy. So first limit we consider as for x, and second limit we consider for y. So y x equal to 0 to 1, y equal to 0 to 2. And we see that both limits are constants. When both limits are constant, so we can integrate any one of them first. So we basically start from right to left. So we solve for y. So integral with respect to that means right to left. So we already mentioned, you have remember. So integrals from right to left. So that means have corresponding integrals with the appropriate limit as right to left. So first we integrate with respect to y. So we write down this as x is equal to 0 to 1, because both limits are constants. So we take as brackets, that means first we solve for y. So you can write down as x plus y into dy and dx. So when we integrate this with respect to y, so all of you have solved the problems related to definite integrals, so you can solve easily. So when we integrate x plus y with respect to y, so x we treat as a constant. So x into dy. So what is the integration of x into dy? So x is constant, dy integration is y plus y dy. So y dy, integration of y dy is y square upon 2. And we take the limit 0 to 2 and write down as dx. Now, when we apply the limit, so first we apply the upper limit, then minus lower limits. So we put the upper limit in place of y. So x is constant, so we put as 2. Here we write down 2. to the square upon 2 minus lower limit. So x into, in place of y, we put as 0 plus, plus means minus, 0 square is 0 upon 2 into dx. So here we can write down this as x equal to 0 to 1. So first term is 2x plus 2 square is 4. 4 upon 2 gives us plus 2. So we other terms is 0. So we write down as dx. Now we have the function in term of x purely. So we integrate with respect to x. So when we integrate this with respect to x, the 2 into x. So what is the integration of x? X dx is x square upon 2 plus 2 dx. The 2 is purely constant, or dx integration is x. So we put the limit 0 to 1. So this 2 cancelled. Now we apply the limit. So 1 square is 1. 1 plus 2 into 1 minus lower limit. In place of x square, we have 0, or minus 2 into 0. So this gives us 1 plus 2 is equal to 3. So the integral value is 3. Okay, so this is the basic question we have solved related to the multiple integral. Now, we move to the further questions related to that. So second question, evaluate integral a to b. Second, 0 to b, you can take the limit as 0 to a. 0 to a, 0 to b, x square plus y square dx dy. So similar, we see that, that means dx dy. So right to left, that means this is limit for x and this limit for y. So first we integrate with respect to y. So we write down as dy into dx. So first we integrate with respect to y. Similar. So we write down this as x is equal to 0 to a, and integration x square into dy. So x square is purely constant. Dy integration is y plus y square is y cube upon 3. 0 to b into dx. So when we apply the limits 0 to a, so this can be written as x square into b plus bq upon 3, minus when we apply the lower limit, so 0 or minus 0 upon 3 into dx. So here we write down this as x is equal to 0 to a. So bx square plus bq upon 3 into dx. Now we integrate this with respect to x. So when we integrate this with respect to x, so we get x cube upon 3 plus bq upon 3 into x, and take the limit as 0 to a. So we get as b aq upon 3 plus bq into a upon 3 minus lower limit, we write down as b upon 3 into 0 minus bq upon 3 into 0. So this gives us aq into b upon 3 plus a into bq upon 3. So here we can take as common ab upon 3. So we get a square plus b square. So this is our answer. So we solve two problems. In both cases, that means both limits are constants. Now we move to the further, that means question number 3. So when one limit is constant and one is variable, so we take one problem related to that. Evaluate integral 1 to 2 and 0 to 3y. 0 to 3y, y dy into dx. So you remember this, that means when variable limit is given into the form of y, so this is obviously limit for the variable x. Okay, so first limit we write down for y, and this limits for x. So because the variable limit given in the form of the y, so means this limit is for x. Now, so in such cases, we solve first the variable limit, then we solve the constant limit. So first we solve the variable limit. So when you solve the variable limit first, so we write down as y is equal to 1 to 2. Integrate first with respect to x. So x equal to 0 to 3y, and y. So when we integrate with respect to x, so y dy work as a purely constant. So we take only dx. So we take only dx, and you can write down as y dy outside of this integral. Okay, so here we do the integration. So that means y equal to 1 to 2. So we write down y this side. So what is the integration of dx? Integration of dx is x, and put the limit 0 to 3y into dy. So when we use the limit, so this gives us y equal to 1 to 2 into y. So we write down upper limit 3y or minus 0 into dy. So this gives us y is equal to 1 to 2, 3y square into dy. So 3y square into dy. So when we integrate this, so this gives us 3y cube upon 3. 3y cube upon 3, or we take limit as 1 to 2. So 3 to 3 cancelled. So when we apply limits, upper limit, so 2 raised to the power 3 minus lower limit 1 raised to the power 3. So 2 raised to the power 3 is 8. 1 raised to the power 3 is 1. So 8 minus 1 is 7. So our answer is 7. Okay, so this is for variable limit. Now, uh, we take the next question, that means question number 4. So for question number 4, we have a variable limit. So evaluate integral 0 to 1, 0 to x square, x into e raised to the power y, dx dy. So here the variable limit given in the form of the x. So this limit will be for y. So that means in terms of x, and this is for limit x. So x equal to 0 to 1 and y equal to 0 to x square. Now first we solve the variable limit. So same thing. So first we solve the variable limit. So we can write down this as x equal to 0 to 1. So integrate first with respect to y. So we write down as, so x we take as outside because x work as a constant when we integrate with respect to y. So we write down as e raised to the power y into dy, and take outside as dx. So first we solve this integral. So when we solve this integral, so we write down as x equal to 0 to 1 x. So what is the integration of e raised to the power y? E raised to the power y integration is e raised to the power y. So 0 to x square into dx. So we can write down this as 0 to 1 x, and when we apply the limit, so e raised to the power minus x square minus e raised to the power 0 into dx. So this gives us x is equal to 0 to 1 x into e raised to the power x square, or e raised to the power 0 is 1 into dx. So you remember, e raised to the power 0 is 1, e raised to the power infinity is infinity, and e raised to the power minus infinity is 0. Now we solve this integral for x. So when we solve this integral for x, so we write down this integral into this form. So x is equal to 0 to 1 x e raised to the power x square minus x into dx. So here we have two functions, that may x into or exponential e raised to the power x square. So we convert this into two integral form. So 0 to 1 x e raised to the power x square into dx minus integral 0 to 1 x into dx. So when we solve this integral, so how to solve this integral? So we can solve this integral by using substitution. So we put x square. So put x square is equal to t. So we write down as 2x dx. 2x dx equal to dt, and dx dx is equal to dt upon 2. So now we talk about the limits. So limits when x is equal to 0. So when we put x equal to 0, so 0 equal to t, it means t gives us 0. And upper limit when x is equal to 1, so 1 is equal to t, so this gives us t equal to 1. So that means limit are remains unchanged. So limits are remains unchanged. So where limits are 0 to 1. Okay, second integral we solve directly. So now we write down this integral as integral t, limits of for t equal to 0 to 1, and x dx. X dx is dt upon 2, or we write down as e raised to the power t into dt upon 2 minus the second integral we solve as x dx is x square upon 2, 0 to 1. So we write down this as 1 upon 2 we take outside, and integration of e raised to the power t is e raised to the power t 0 to 1 minus 1 upon 2 taken outside, and when we apply upper limit, 1 square is 1 minus 0. So this we can write down as 1 by 2 e raised to the power 1 minus e raised to the power 0, or minus 1 by 2. So this equal to 1 by 2 we take common. So e raised to the power 1 is e minus 1 and minus 1. So this gives us 1 by 2 and e minus 2. So this is our answer. Hope you understand. Thank you.